have just a couple more topics to round out our discussion of the electric potential. The first one is an alternate unit, which is called the electron volt. So if you were to say have a charged particle start off at some position, and at that position there is some sort of potential, let's call it 4 volts. The electric potential at that point is 4 volts. And I have, say an electron or a proton that has some charge E. And then it moves through some sort of change in potential to a line that says maybe positive 5 volts. So an electron volt is the energy gained or lost by going through that 1 volt potential difference. So this is a delta V of equal to 1 volt. So since an elementary charge has a value of 1.6 times 10 to the negative 19th coulombs, so when you plug that into your change in potential energy is Q times delta V, that gives us that the energy would be 1.6 times 10 to the negative 19th joules. So that is our definition of EV. And this comes up, this is used a lot in chemistry. So if you've done electric potentials with electrochemistry, you might have seen the unit EV. And that's because a joule's amount, 1 joule's worth of energy is a whole lot of energy for situations like this. So this is just an alternate way to do that. It's just equivalent. It's not something you're going to see very often in physics because we tend to work in SI units and joules is the SI unit of energy. But sometimes it helps to make your calculations a little smoother because you don't have to convert to joules. So the next topic is equipotential surfaces, and this relates to the lab that you have hopefully already worked. So it's possible to move a test charge from any point to another point and do absolutely no work as long as those 2 points have the exact same potential. So this is the idea that your work is equal to the change in potential energy and negative the change in potential energy, and then that change in potential energy is equal to Q0 times delta V. So if you go from one equipotential point to another, so 2 lines of equipotential mean equal potential, then delta V would be 0, so the work would be 0. So we define any surface that has this equal potential to be an equipotential surface. Now this could be a 2D or a 3D surface. It could be some normal geometric shape or anything else. So we can map those out like you did in your lab. And so as long as you start and end a particle on that equipotential surface, no matter what happens in between those 2 points, you know there'll be no work done and therefore no change in energy. So here are a couple examples of those equipotential surfaces. So the first one on the left is for a point charge. The equipotential surfaces are represented in this image with these blue lines. So a couple of things that we notice that these are going to be spheres. In 2 dimension they look like circles, but they're actually going to be spheres. And that's because the potential of a point charge is KQ over R. And so for any one source charge, Q, that tells us that to have an equal voltage, you just have to have the same radius. So if you're at the same radius, you're going to have the same potential. So you're going to end up with spherical surfaces. Now, we also notice that those potentials are closer together the closer you are, and they get further apart the further away you are. And that's related to your electric field strength, because remember that our electric field strength, our electric field is equal to negative dV/dr. And if you're looking at small scales, we can approximate that strength, the magnitude of that, as just the change in potential over the change in radius. So we know that our electric field is going to be stronger the closer that we get. So that way you're going to go through more changes in delta V in the same radius when you're close than when you are further out. Okay, so we can see that relationship with those equipotential surfaces. Now, the one over here for the 2 positive point charges is a little more complicated. because it's not just that it's the sum essentially of all of those potentials. So what you end up with is kind of this nice infinity symbol here in the center, which is kind of interesting. And then these potentials actually loop around and connect. So if you were to calculate the potential at each one of those points on that particular curve, they would all be the same. Because that is the sum of the potential due to the two different charges. And those will always add up because they're both positives. If you had a dipole with the positive and negatives, then you are going to have potentials that do cancel out in the center because they will be in opposite signs. So some cool things that we can see there. You can also see the same relationship that your strongest electric fields are going to be where those equipotentials are closest together, and your weaker electric fields are going to be where those equipotentials are further apart. So in this example, we have a map of equipotentials. So each point represents a particular potential value that is being caused by 2 point sources. Our point charge sources are going to be Q1, which is unknown, and Q2, which is 2.0 nanocoulombs. So the way I read this is I can assume that if I was to pick any random point, so I could pick like this point right here, I'll call it point P, that the potential at point P has to be due to the sum of the potentials due to each of those charges. So Q2 here is going to be acting at some radius R2, and Q1 is going to be acting at some radius R1, and they are both creating potentials. Q1 will create a negative potential, Q2 will create a positive potential, and we will end up with some value there. So that's how this map is created, is essentially by measurements or calculations based on those assumptions. When I read this map, the other thing that I want to pay attention to is the scale. So my scale here is 0.5 meters from dark line to dark line. So that means one single square here is going to be 0.1 meters. I can learn a lot about the potential just by looking at this map. I can also learn about the electric field. So for example, I know that my electric field is going to be strongest when my potential lines are close together. So that's going to be at that point right here. And it's going to be weakest out here in this area where there's a lot of space in between those potentials. I also noticed that I have a 0 volt line here. That is a line where everywhere on that line, the potentials due to the two charges are canceling out. I can see that I have negative potentials over closer to Q1 and positive potentials closer to Q2. So that tells me that Q1 is going to be negative and Q2 is positive. I know that at least one of them has to be negative because if they're not, it's impossible to get negative values and it's impossible to have a 0 potential point. So we're going to work through a bunch of different problems. So the first one we're going to work through is this one. We want to determine the value of Q1. So I can technically use any point on this map to solve this problem. Because I'm assuming that these are source charges, I know that the potential of a point source charge is going to be KQ over R. So I can use that information. And then as I said, we're going to have to sum up the potentials due to both of those charges at a point. So I could pick any point to do this, but I'm going to choose point B. The reason I'm going to choose point B is for 2 reasons. First, it is on the 0 volt line, so that's nice and easy. So that means actually the net potential is 0. So that'll simplify my math down a little bit. And the other reason is point B is actually on that x-axis and on a grid intersection point. So it's going to be really easy to find my R values. So with Q2, I'm going to have my distance R1, or sorry, that's R2. I don't know why I want to do that, probably because I keep doing that one first. So that's going to be R2 right there. And if I look at my scale, I go from one dark line to the second dark line. So that's going to tell me that R2 is going to be 1.0 meters. When I look at Q1, that's going to be here, and R1 is going to be this entire distance to that point. And I go through, that's 0, 0.5, 1, 1.5, 2, 2.5. So R1 is going to be 2.5 meters. And then Q2 is known, but Q1 is not. So what I'm going to do is I'm going to use my information to write a potential equation. So the potential at B is going to be the sum of the potential due to charge 1 plus the potential due to charge 2 at that point. But that's equal to 0 because point B is the 0 potential line. And then if I solve for V1, I find that V1 is equal to negative V2, which makes sense because they're canceling out. I can then sub in my equation for the potential of a point charge. So I get KQ1 over R1 is equal to negative KQ2 over R2. Those K's are going to cancel, so that's a nice simplification right there. So then I can solve for Q1. Q1 is going to be negative Q2 R1 over R2. I can then plug in numbers. So Q1 is going to be negative Q2, which is 2.0 nanocoulombs. In this case, I do not need to convert to coulombs because this is a ratio, so I'll just get an answer out in nanocoulombs. And then I have R1 on top. R1 is 2.5 meters. And R2 is on the bottom, which is 1.0 meters. So that gives me a value of negative 5.0 nanocoulombs. So in this case, we want to determine the electric field strength at point D. Now, point D on our map is this point right here. Now, my electric field and my electric potential are related by the equation E is equal to negative dV dr. But in order to use this function, I actually have to have a function v of r in order to take a derivative. I don't have that. I have just a map of potential values. However, the reason they chose point D for this problem is D is equally between these two potential lines, and those potential lines are kind of close together. So what we can do is we can do an approximation. And we can say that the magnitude of E is approximately equal to the absolute value of the potential difference over the change in the position, basically the separation distance between those lines. Now, that's only going to work because the change in distance is small compared to the change in potential. This is also an equation, an approximation that we often use between parallel plates. And if you kind of look, it's almost like in that small section. It's like, yeah, you can assume like on a small scale, it's kind of like a parallel plate. So this equation is actually pretty easy to use then, because delta V is just the difference in potential, and that's a 20 volt line and a, well, negative 20 volt line and negative 24 volt line. So the magnitude of delta V is just 4 volts. And then looking at my grid, each individual grid line is 0.1. So the separation distance between those is just going to be 0.2 meters. So therefore, if I want to find the magnitude of the electric field, that is going to be the magnitude of delta V over the magnitude of delta R, which is just going to be 4 volts over 0.2 meters. When you calculate that out, you get 20 newtons. Whoa, that's not a 20. 20 newtons per coulomb. So not too difficult once you know the trick. Now you know the trick, so you'll be able to do it in later problems. So in the next one, we want to determine the electric flux for that 0 volt potential line. So here's that 0 volt potential line, under the assumption that it represents a spherical Gaussian surface. So we can picture that this is a spherical surface that is coming out. Notice that Q2 is not in the center. The center of that surface is going to be somewhere over here. Q2 is a little off center, and that's okay, because to do Gauss's law, it doesn't matter where Q2 is as long as it is inside of the Gaussian surface. So our definition of electric flux, according to Gauss's law, is Q enclosed over E naught. So Q enclosed is just going to be that 2.0 nanocoulombs. Now, we do need to be in SI units because E naught is a constant that is in SI units. So to do this one, we would actually have to convert. So we would plug in the 2.0 times 10 to the negative 9th coulombs for our nanocoulombs. And then that E naught is our permittivity of free space, which is 8.85 times 10 to the negative 12th. And that, I don't remember the unit on that one. I think it is coulombs per Newton meters squared. Coulomb squared. I think it's like that. It's the opposite of K, the opposite units of K. And then when you plug those in and calculate, you should get this 226 Newton meters squared per Coulomb. So that is our flux. So that only works actually it would work for any of these surfaces, but the sphere is the only one you can imagine. You can imagine like this one here. That one would be kind of fun and funky. That'd be like some sort of three-dimensional egg shape. Because these are not two-dimensional surfaces. Our Gaussian surfaces have to be three-dimensional in order to fully enclose the charge. All right, so this next one, we need to calculate the work done by the electric field on a proton that is released from rest at point A as it moves to point E. And we want to do this in electron volts, so we get a little bit of practice using that electron volt unit. So point A is here on the positive 4 volt line, and point here is on the negative 4 volt line. So when we're doing work, we have a lot of different ways to define work. We could define work as equaling the negative integral, or just as the integral, sorry, not the negative, of force of FDR. So, and you'd have, of course, technically do that as a dot product and so forth. But because we're dealing with a conservative force and conservative fields here, we can also define our work as equal to our change in kinetic energy was equal to negative our change in potential energy. So when I approach a problem and I'm not sure exactly what to do, I have to think about what I know and what the assumptions are. So the first thing is I have no clue what that force function is. I could find it at every point, but the problem is that force is going to be different everywhere between A and B. Because we're getting further away from the charges, the forces are going to be getting smaller. So I don't have a function for that. I don't want to write a function for that. So instead, if I'm doing work, I'm going to take advantage of the conservation law there. So I don't know anything about the speeds, but I can learn information about potential energy from my electric potential map. So work is going to equal negative the change in potential energy. So I know that by definition, my change in potential energy is equal to Q0 times my change in potential. So that's really nice because this is dependent only on the starting and ending positions in this field. So my work here is going to be negative Q0 times V at E, that's my ending potential, minus V at A. Sorry, I didn't really leave a lot of space to be able to write these on here. So my work is going to be Q0. Now, because I want to be in electron volts, I am not going to plug in 1.6 times 10 to the negative 19 coulombs. I'm just going to leave that as E. So I get negative E. And then my V at E is negative 4 volts. Minus my V at A is positive 4 volts. Sorry, negative 4, positive 4. That did not come out well. Give me just a sec. Fix that up. Positive 4 volts. So negative 4 minus 4 is a negative 8. But I have this negative out in front, so I get a positive 8 electron volts. Isn't that nice? So you don't plug in for E, you just leave the E there, and then make sure that your potential difference is in volts, and that gives us our answer. So we have a positive 8 electron volts. Now, what does that positive tell us? That positive tells us that our work going from A to B would result in an increase in speed. This is a proton, it's a positive charge. And that makes sense because it's going to be most strongly influenced by this positive charge that's right here because we are in the positive volt region. So that means that the charge is going to experience a force that is to the right, which is, in the same direction as the displacement vector. And that is what's going to give us our positive work and would cause our proton to speed up. Now we want to calculate the speed of that proton once it is released from rest at point A and it gets to point E. So I want to find what is the speed here at point E. Well, I can still stick with our conservation laws. So I know that the work that we found is also equal to the change in kinetic energy because we have a conservative field. So that change in kinetic energy is going to be the K at E minus the K at A. But we are assuming that our kinetic energy at the start was 0 because it was placed at rest. So my work is going to be 1/2 mv squared. Now that is now the lowercase v for speed. That is not our capital V for volts. And I do run into a problem here because my work was not in SI units, which would be joules. So when I do go in and solve for this problem, I am going to have to convert my electron volts back into joules. To do that, I multiply by 1.6 times 10 to the negative 19th. And that's basically joules per electron volt. So that was how you would get that conversion in. So coming back over here into our equation, if I solve for my speed, I would multiply by 2 and divide by m, and that's going to equal v squared. So v is going to be the square root of 2 times my work over m. And so when I plug in, I'm going to have to do 2 times my 8 electron volts times my 1.6 times 10 to the negative 19th joules per electron volt. And then I divide by the mass of a proton, which is 1.6. Sorry, 1.67 times 10 to the negative 27th kilograms. So then I divide by the mass, which of my proton, which is 1.67 times 10 to the negative 27th kilograms. And when you plug that in, you should get about 3.92 times 10 to the 4th meters per second. So it's going to accelerate. It's going to get faster and faster the further it goes. So my speed is going to continuously be increasing. But as I'm getting further away from those charges, my acceleration is decreasing. So it will be getting faster, but at a slower and slower rate over time. All right, so in the next problem, we have an electron released from rest at point B. We want to know in which direction does the acceleration of the electron point at the instant it is released from rest. So when I'm looking here at point B is on the 0 volt line. So you might be tempted to think, well, it's on the 0 volt line, so it's not experiencing a force. But that's not correct. We have to remember that our electric field is based on the rate of change of potential. So our electric field is equal to negative dV dr. So in the region around it, we do have a changing potential. And we know that our electric field points in the direction of decreasing potential. So our electric field at point B is going to be pointing to the right because that's where our decreasing potential is. Now, we're placing an electron here at point B, and we know that the force on a negative charge is going to be in the opposite direction as the electric field. So even though the electric field is going to be to the right, the electric force on that electron is going to be directed to the left. And because our force is mass times acceleration, whatever the direction of our force is the direction of our acceleration. So the electron is going to experience a force to the left. And this does actually make sense because if our proton is moving to the right in that region when placed at rest, it makes sense that electron would experience an acceleration in the opposite direction. So now we want to actually draw some representative electric field lines. So you should have had practice with this in the lab if you've worked with the lab already. But generally what we do is when drawing these field lines, we start on one of the charges. I usually start on the positive charges because I know my electric field will start on positive charges and go towards negative charges. So I'm going to start by picking one spot anywhere, and I'm going to draw a line that is perpendicularly away from that charge. So I'm making sure that I'm making a 90-degree angle right there with the surface of the charge. And I'm going to head kind of straight towards that first line, but I have to make sure that I cross all of my lines at 90-degree angles. So I'm going to go here in the direction of decreasing potential. I'm going to try and cross at 90 degrees right there. And still going in decreasing potential, kind of go 90 degrees there. And notice this is ending up with kind of a slight curve here as I'm trying to make those to go through at 90 degrees. Now, 90 degrees here is going to be nearly vertical, so I'm going to have to make kind of a big curve right there to kind of come out. I'm going to probably curve that a little bit more kind of along the way. And then that's going to be going away like that. So I could then pick a different spot. Let's pick this spot right here. This one's nice and easy because it's just going to go straight away like that. This point's kind of fun and wonky because that's where our electric field actually switches kind of directions at that point. Not the electric field, but the potential kind of wraps back in on itself. But we're still going to be going kind of perpendicular away from that location. I could do a similar line down here. So let's pick one. I don't know, let's actually pick one kind of coming this way. So I'm going to come off here like this. And once again, I'm trying to cross each one of these equipotentials at 90 degrees. So that's forcing it to kind of curve around as I go. And notice that's actually curved me kind of back towards Q1. So I'm going to assume that this actually then continues and kind of forms back there on Q1. I didn't quite come in 90 degrees to Q1. So let's try to see if I can come off a little bit better like that. And then I could maybe pick another point over here and go straight across. That'll come straight across like that. And then if I keep doing this, you should have at least 6 field lines as you go through. You should try and make those cover as big of a range as possible. I think 8 to 10 lines usually gives you an even better kind of understanding of how that field's going to be. But you want to kind of represent kind of all of the different parts of that field and how that comes around. So you can kind of represent what is going on with that field. I might pull some in this way to have those kind of covering the backside of that charge. And that would be my field.
So we know that conductors have special circumstances when we talk about the electric field. And they're going to have different relationships when we look at electric potential. So the most important thing to realize with our conductors that is new is that in a static situation, so a situation in which we put charges onto a conductor and allowed them to move around until they've reached equilibrium, the surface of the conductor is an equipotential surface. It doesn't matter how wibbly wobbly that surface is. Everywhere along that surface, the potential at the surface is going to be constant. So we're going to look mostly at things like spheres and so forth, but that has to be true for every single conductor. But what value is that constant value is going to be something we can derive. And then the big question is what's going on inside. The reason this is a big question is because with the electric field was always zero inside the conductor. So that was something that always has to be true for a conductor. For potential, the thing that always has to be true is that the potential at the surface is always constant. So we can use our equation for the relationship between the electric field and potential. E is equal to negative dV dr to kind of figure out this relationship. When we take the rate of change of a function in calculus, that is the same thing as a derivative, and that is the same thing as the slope of a graph of that function. So what this tells us is that if we have a graph of potential, whatever that graph is, so some wibbly wobbly graph, when I take a look at any one instant, so I could look here or I could look here, the slope at the point is equal to negative the electric field. Or electric field is equal to negative the slope, either way. So there's a relationship between the slope and the potential. So what kind of graph would give me an electric field equal to zero? So I would need the slope of the potential graph to equal zero. So the graph that would give me that is if my potential was a straight line. If that V is constant, then there is no slope. The slope of this line is equal to zero. And that is what would give me my electric field equal to zero. So this tells me that if I have an electric field inside that is zero, my potential must always be constant. So we can now write a rule that says our potential is always constant inside of a conductor. That goes along with our electric field is always zero inside of conductor. And we also know that our surface of the conductor is an equipotential. So there also has to be a constant surface. The problem with this idea is when you're integrating, because this actually, you have to work the opposite direction. We could define that our potential difference is going to be negative the integral of E, we're going to use dx in one dimension. So if you were to try and integrate 0 with respect to x, the integral of 0 is just a constant. You would get with the indefinite integral, you would get a constant. So technically, that integral represents every possible graph where you could have a potential that is constant. So I could have this potential where V is 1. I could have this potential where V is 2. All of these have a slope equal to 0 and would have electric field equal to 0. So I do know that that potential is constant, but what value is that potential going to have? Well, we basically said, why not make that potential equal to whatever it is at the surface? Because that is what made sense to them at the time when they made that definition. So you can do that with boundary conditions. So when we take a look, we assume that the value of the potential inside the conductor is going to be chosen to match the surface. So here we have a sphere. We can assume that this is a positively charged sphere. And this is the magnitude of the electric field. So I can look here at this position R. This would be R equals 0. And I can compare those graphs. This point here would be R equals R. So when I'm looking at the electric field, I can see that inside the material of my conductor, when R is less than R, my electric field is 0. I can see at R equal to R that I'm going to have a potential that is at a maximum, and then it's going to decrease proportional to 1 over r squared as you get outside of r. On the other hand, my graph of my potential is going to show that when I am inside the material of my conductor, that the potential inside is constant and equal to whatever value it is right there. It's actually a continuous function. And then instead of being proportional 1 over r squared, it's proportional 1 over r for as you go further out. So the electric potential decreases at a slower rate than the electric field does outside. So you have to be very careful when you're comparing conductors in terms of the potential and the electric field, because the electric field is 0 inside the conductor, the electric potential is constant inside the conductor, and we assume that the potential value that is constant inside is equal to whatever it was at the surface.
Our very last topic is going to be about conductors. We've already talked a little bit about kind of how the charges on conductors behave, but now that we have potential, we have a little bit more information that we can use to solve problems. So what we assume is in a static situation, so when we say static, that's a situation in which we've placed charges on to our conductors and allowed them to move around and reach equilibrium. We always assume that the surface of a conductor is an equipotential surface. This doesn't matter how wibbly wobbly the conductor is. Every point on the surface of a conductor is going to have the exact same potential. But what is that potential going to be inside of the conductor if there's a surface charge? We know that inside a conductor, the electric field is always 0. We've now learned that the surface of our conductor has to be an equipotential surface, but what is going on inside of our conductors? So our electric field inside of 0. And so what this tells us is based on our equation in 2 dimension, or actually 1 dimension, is that E is equal to negative dV dx. Well, that's not potential. So if our electric field is 0, that means dV dx is 0, or V is constant. So I can picture my electric field, okay, by being defined by some function. Maybe it is an inverse square relationship. I don't know. But what I know is that electric field has to be related to my potential by actually being the slope of that potential graph. So if I was to know my potential and give it some sort of function, let's give it, say, a positive slope right there. I know that my electric field would have to be equal to the slope, because that's going to be equal to dV dx, negative dV dx. So if I have a constant positive slope, I know that my electric field will have to have a constant negative value for that same position, because it's negative of whatever that slope is doing. So if my electric field is 0, how do I get a potential that would give me a 0 electric field? Well, if instead of being a positive slope, my potential was a constant value, the slope of that would be 0, which means dV dx would be 0. So if I have a constant potential inside, that is going to give me my electric field equal to 0. So I know that on the outside, I have an equipotential surface, and inside, we now know that we have to have a constant potential inside of our conductors. So here is an example. So with that constant, when you integrate, so if I was to integrate, you are going to get a function where V is equal to negative E dr. When E is 0, what you are going to get is a constant. That constant of integration. And so with this constant of integration, it could represent any value. But what we want is for that constant of integration to make sense. So we always assume that our constant inside is equal to whatever the surface value is. So our potential inside is constant, and it is equal to our surface value. So here is a conducting sphere. So we can see that with our electric field, when you are inside the radius of the sphere, you have no electric field. Our electric field, because this is positively charged, would be radiating out equally in all directions. That means that it is going to have a decreasing magnitude as it goes away. That is going to be getting smaller. So if you were just to picture the positive quadrant over here, quadrant 1, so your electric field is going to be 0, and then it's going to be at a maximum at the surface, and it's going to have that inverse square relationship as it leaves. Now, the potential, on the other hand, is going to have an inverse relationship. So this is going to be a 1 over r function on the outside, and you're going to be at a maximum value here. But when you are inside the material of the conductor, our potential is not 0. We assume that it is constant in whatever you have here. And if you were to take the slope of this graph, the slope of this graph would equal the graph of the electric field. So you'll see that in your derivation packet. Now, not every situation has to be very complicated, but we can go a little further than what we did before with kind of conductors. So we worked problems previously where we said that if your two charged conductors are brought in contact with each other, the charges are going to move so that the conductors will reach equilibrium. And if those charges have the exact same size, they're going to end with the exact same charge. So we only worked problems in our previous unit for conductors that were the same size. So if I say started here with a positive Q on one and a negative 2Q on the other side, and I were to bring them together, my total charge here at the start is equal to a negative Q. So when they separate, they're each going to end up with a charge of negative Q over 2, because that total charge is going to get distributed equally between the two so that they both have no net force and no net electric field inside. But what about if their radius is different? If they have a different radius, then they are not going to end up with equal charges, because radius is a big factor in our definition of electric field and also electric potential. So a couple things are going on. So the first thing is our charge must still be conserved. So whatever charge we have at the start has to be the charge at the end. The other thing that has to be true is that all points along the surface of the conductor, while they're in contact, have to have the exact same potential. So that when you bring them together, the large one and the small one, this entire surface here in 3 dimensions ends up being one big equipotential surface. So that tells me that the potential at any point on the surface of these spheres has to be the same. So the potential of the large sphere at the surface has to be equal to the potential of the small sphere at the surface. And we know that our total charge must be conserved. So this is actually giving us a system of equations with 2 unknowns, which are going to be the charges of the 2 spheres at the end. So what we can do is for either of the spheres, we can find the potential at some radius r. So there's different ways to go about doing this. This formula is on your formula sheet, so it's not something you have to have memorized, but it's always good to practice. So if I was to practice this derivation to find the potential at some r, I would assume that I'm looking at the potential compared to infinity. and I'm looking at the potential at R. So I'm going to compare the potential at R to infinity. And by definition, that's going to be negative infinity to R e dr. So that is integrating our electric field. Now, we already know the electric field for a point charge, but this is a sphere. It's not a point charge, it's a sphere. So what we do is we need to sub in for the electric field. Well, we learned previously that when you have a conducting sphere, when you are outside the radius of the conductor, your electric field is just equal to that of a point charge. Same formula. So we can plug in kq over r squared for that electric field. And then we are also going to assume that our electric potential at infinity is 0. That's going to be our reference point. So that's going to be able to give us, instead of a potential difference, a singular potential value. So then what I am doing here is, the other thing I forgot to mention is I am flipping my limits. So to get rid of this negative out in front right here, I did flip a limit to get it from R to infinity. There's no particular reason to do that, just to get, I don't like having negatives sticking out in front before I integrate if I can avoid it, because I often forget the negatives, but that's not a necessary step. So then when you integrate, your KQ can get pulled out in front. So you're integrating from R to infinity of basically R to the negative 2 dr. So when you do that, you are going to end up with KQ times a negative 1 over R to the negative 1. And we have to evaluate that from R to infinity. So that is now going to bring us here to this point. So I wanted to show you the calculus steps that were kind of in between leading up to that point. So when we get to that point, we can then plug in our limits. So you should always show the substitution of limits. So that's going to give us negative KQ over infinity minus negative KQ over R. And of course, a constant over infinity goes to 0. So that is going to give us KQ over R, because this negative and that negative are going to cancel. So awesome. What we've just done here is we've just proved that the electric potential for a sphere of charge is going to be the exact same as the potential for a point charge, as long as R is bigger than the radius of the sphere. So we can actually use that same equation. And that equation is on your formula sheet because it's for a point charge, and now we know that it also works for a conducting sphere. Isn't that fun? So once we know that, we can then write equations for the small sphere and for the large sphere. And I really should have written some subscripts here. So that's my small sphere. That's V for my large sphere. And we have our charges. So we assume that those have to be equal, so we can set those equal to each other. So we can walk through that. So setting those equal to each other, when they are in contact, we get KQ1 over big R for this first one is equal to KQ2 over 2R for the second one. Once again, the K's are going to cancel, and the big R on the bottom is going to cancel. So that gives us that Q1 is equal to Q2 over 2. And conceptually, this makes sense because our larger sphere had twice the radius. It's going to have a different charge in order for those potentials to be the same. So bigger sphere, bigger charge in order to have the same potential as the smaller sphere. The problem is we don't actually know Q2, which is going to be that new charge. But this is where our other equation can come in. To find those new charges, we are going to use the conservation of charge. So we know that Q1 has to equal Q2 over 2 from our potential derivation. And we also know that Q1 plus Q2 has to be negative Q, because negative Q was our starting total amount of charge. So what I can do, and I'm not sure why I did this in this order, but I decided to solve for Q2. And I solved Q2, subbed Q2 in there because I guess I wanted to find Q1 first. So then I get Q1 plus 2Q1 is equal to negative Q. Combining those together, we find that Q1 is equal to negative 1/3 of our total charge Q. We can then sub in back here, and we find that Q2 is equal to negative 2/3 of Q. So we check that, and we can see that Q2 is double of what my value for Q1 is. There are ways that you could rationalize this using proportions, using the fact that our potential was equal to KQ over R, so that if you have double the radius, you'd have to have double the charge as well, and then you could think about the ratios of the charge for that. But this is kind of a more robust derivation to kind of prove that that is the way it is. So those are nice little problems that you can solve that kind of build on what we did very early in the course, but now giving us the ability to solve a wider range of problems.